The internet is broken. What used to be a decentralized network powered by millions of self-hosted servers is all but gone. Today, every image you share, every video you watch, every form you fill, flows through centralized networks controlled by just a handful of companies. But there's a change coming, a monumental shift. And at aleph.im, we're supercharging the transition to a new decentralized era. An era that provides fully decentralized cloud storage, computing, and identity services, powered by incentivized self-hosted servers. Built from the ground up, our unique architecture blends both off-chain and on-chain technologies to support an ever-growing constellation of blockchains and companies. We've built the tools that allow you to store any file of any size on our proven decentralized network. Protect your precious NFTs securely on our network for eternity with our pioneering backup dApp. Unleash the power of our decentralized virtual machines, allowing you to run dApps in any language that can also read and write to blockchains or be triggered by off and on-chain events. Be empowered to store, build, and launch incredible things in this new era of decentralization. Join us at aleph.im.
Nice having you all here. We've got some people watching in the stream already. It's pretty nice. So yeah, our first workshop about virtual machines. Really excited about it. First of all, wanted to thank everybody who's been helping to get us there, with Hugo and the whole team of developers making this happen. So really nice, and really glad that we can share this now with you guys, because it's a big milestone on our roadmap. So what are we going to do today? It's we have the workshop that Hugo is presenting about virtual machines on Aleph, and we have a Q&A, and you can, during the workshop, you can ask questions if you want. We will be answering that. You can do it through the Twitch chat or the link that I shared in the Twitch chat on Telegram. So I will be monitoring those two, and then we will go through the questions and answer them through the workshop with you guys. But with no further ado, I'm going to leave the word to Hugo, who will get you started with the VMs.
Thank you, Claudio. So this is a developer-oriented workshop. The first part will be a presentation of the architecture of how the VMs run, what's under the hood, and then we will see an example on how to create a VM using Python and host it on Aleph, and then accessing it and making it available publicly. So let's get started with the slides that I have for you. So first thing, let's understand how the virtual machines work. Then we'll create a simple Python example on the Aleph VMs, and then if we have enough time, we'll do the same thing with a Rust program, and will show you how you can use any language to make VMs on Aleph. At the moment, Python is the main supported language. We will add some more in the future, but we are focusing on making Python great first, so you can have a great experience with one language. You can still have the flexibility to add others. We're always welcoming contribution from the community. If you think other languages should really have also first support, it's an open source project. In the link below here, you can see the documentation about this workshop, the tutorials on how to create VMs on Aleph. You can, so we'll be following these tutorials, and everything I'm saying, I'm showing, I will be demonstrating here in this workshop is also documented, written right there. So that's the main reference for you to have a look at. So if you go on the Aleph VM repository, click on tutorials, you will get there. First, for the practical part of the workshop, there are a few requirements that we communicated about beforehand. You will need a recent version of Python and pip, preferably on a Debian or Ubuntu system. If you don't have one of these, you can run it in a container, in a VM, that's fine. You will need a cryptographic library to sign the messages that are sent on Aleph. And you also need the SquashFS user space tools that are used to zip the programs that are published on Aleph VMs. So instead of using zip, we use SquashFS, which gives us better performance to read the files inside these archives. Let's explain a bit how Aleph VMs work. So the main architecture is you have internet clients on browsers in the apps that need to have some backend and want it to run on Aleph in a decentralized way. So the clients connect via HTTPS to the VM supervisor. And the VM supervisor is in charge of launching the VMs, stopping them. And these VMs, they have access to the internet, they have access to an Aleph node that's the closest from the Aleph supervisor, from the VM supervisor. And so globally, that's how it works. There will be other ways to start the VMs later, but the main way at the moment supported is you have an HTTP request, it will start the VM, your program will handle the request, do whatever is necessary, and then answer with a proper response to the client. So something about this is you might be considering is the latency, and that's why Aleph is using something called fast micro VMs. So it's based on Firecracker, a technology developed at Amazon, and these VMs they boot very fast. In less than half a second, you have the entire system up running. Your program is executing, maybe has already finished, and the response is already on its way to the client. To do this, these micro VMs, they use hardware acceleration using Linux KVM, and they are optimized to be as fast as possible. And to do this, what has been done is they don't virtualize everything on a PC. If you're using a PC or if you're using a virtual machine like VirtualBox or VMware, it's emulating an entire PC with a display, with a graphic card, with USB keyboards, all kind of stuff you don't have on a virtual machine, and you don't really need to run a program on a server anyway. So it's not doing all of this. It's just doing the bare minimum. You have network drivers, you have network devices, you have some I/O to communicate with the host, but you don't need to know about USB. And so these Firecracker micro VMs, they don't know what USB is. They don't care. They don't have access to it anyway. They don't need it. But that means they can run really fast. However, that means also that you can only run Linux on Linux with these. They really depend. They're optimized to use Linux KVM from the host. And within the VM, they're optimized to run with Linux as well. And if you want to run them on your own system, or if you want to have your own nodes to run VMs, then you have to know that they only support Intel CPUs at the moment officially. There is a developer preview for AMD and ARM, and they appear to work, but there is no guarantee that everything is supported. So it's mostly, at the moment, Aleph VMs only support 64 bits x86 programs. Let's have a look a bit at the components of these VMs and how they work. So here we have a bit more details than in the previous slide, and the main components and the main environment to run these VMs. The first part is the kernel. So this kernel is running inside the VM, and it's an optimized Linux kernel that we built, removing the drivers for a lot of useless things to make it run much faster than if you were to use a fully bloated Linux kernel like the ones you're using on Ubuntu by default, for example. The second part is the runtime, and the runtime is a customized Linux root file system. So we customize it to make it smaller, to have everything you need for Aleph to run. Then the third part is the code archive that's containing your program and maybe some additional data settings that you're shipping next to your program. And finally, a small part that is still important to consider is the jailer, and that's something you will not really see, but it's an extra layer of security. We really don't want one VM to be able to access anything from another VM. So we want to isolate the programs as much as possible with the greatest security we can provide. And to achieve that, the jailer is a process that's a bit like a container, like a Docker container, that wraps the VMs in an additional layer of security. And on the left of the schema here, you can see that the VMs have access to the internet, so everything on the internet can be reached. Let's talk a bit more about the runtime. So the runtime is the Linux root file system, configured to run programs on Aleph. It has some pre-configuration specific for Aleph. It has the aleph-client libraries pre-installed. It's also optimized to be small enough so that it doesn't require too much overhead. And it contains a special init system. The init system is the program that's in charge of running all the other programs. And this one is in charge of doing one thing. It's to run your program. So when it's booting, it will directly run your program. And there are two ways it will do this. Either your program is written in Python, and then it will use the ASGI interface to talk with it, which is a standard we'll talk about just a bit later. Or your program is a binary or a script, and you'll just run it and expect it to accept HTTP request on port 8080. So you can write your VM in any language you like. It's language agnostic. As long as it runs on Linux, it's fine. At the moment, we have an officially supported runtime, which is based on Debian 11 that was released this summer, contains Python and a lot of other libraries that are useful to interact with Aleph. So to launch your program, the VM will use what we call an entry point. The entry point is a small setting that says this is how you launch the program. If it's a binary, this is the name of the binary you have to launch inside the archive. If it's a Python ASGI program, it means this is the application variable you need to use as an entry point to pass all the requests to. If you're using Python with ASGI, so the asynchronous server gateway interface, that means you can use any ASGI compatible web framework such as Django, FastAPI, Quart, which is similar to Flask you may have heard of. They just work on Aleph as they would work with other HTTP servers that talk ASGI to the program. And if you're using Python, we have the aleph-client library built in, so you can directly access extra settings, talk with the host to have extra features that you cannot be available just inside the VM because of security reasons. So we have this API that's accessible directly using the aleph-client library. And it's very fast. It's really optimized also to launch your Python program really quickly. The other entry point you have is the HTTP server. So as I said before, you can write your process in any language. You just have to listen to HTTP requests on port 8080. If you want to access these advanced APIs, for example, to have the host signing messages that say, well, this message was really executed by this VM on that host, for example, you can still do it, but then you need to interact with the vsock sockets. So you need a library that allows you to talk using vsocks with the host. And that's a specific kind of sockets that is very optimized. It's really fast and really dedicated for the VM to talk with the host. You can have VMs that do not have internet access, for example, to make them more secure or more reproducible. And in that case, they can still access this host API. They still have access to the Aleph network, but they don't have access to the rest of the internet. That also allows you to know exactly which Aleph node they will talk to, because it's already pre-configured. Next, the other part you need to consider is something we call volumes. So you can extend the VMs by specifying additional volumes that will be mounted in the system. For example, you have some data, some static data, or some libraries you want to access from your program, but are big. They don't change very often. You can put them in a read-only volume that you only update now and then, and that is mounted inside the VM. An example of this as well is the Python virtual environments, or if you're doing JavaScript, the node modules directory, which can be quite big, contains all your libraries, and you're not changing it very often. You don't want to upload 250 megabytes of node modules every time you change a line of your program. So you can manage these independently, even have third parties managing them. To update a volume, you need to just publish a new version of it, referencing the previous version and signing it with the same key. So these are the read-only volumes, very useful for all these heavy libraries. Then we have the host persistent volumes. So these are quite the opposite. These are writable volumes that are persisted on a node. So if you run a VM on a node, and then you call that VM many times, it will be turned off, launched again, and that's fine. And it will always have access to this volume on the host, as long as the host didn't decided not to remove it, garbage collected because it's too old, or delete it because it's taking too much space. So there is no strong guarantee that it will still be there, but if you want to store a cache and to process data, it's a great way to keep the data alive longer in a cache locally on that node. Then you have ephemeral volumes. These are simply used as a way to have some temporary storage while your VM is running. You could put everything in RAM, but that would be too expensive, so you can have a disk that only lives while your VM is running, and then it will be deleted afterwards. And finally, something we're still working on is the store persistent volumes. So these are volumes that are persisted, but not on the node itself, but then they are published on Aleph, so they're persisted on the Aleph network. However, there are some constraints you need to be aware of. It is that an Aleph VM will always use the last version of store persistent volumes. So if two VMs on two different nodes created a volume at the same time, then only the last one will be kept, and the other one will be archived on Aleph, but will not be available directly. You will need an extra process to access this data from this conflict. So here we have a more detailed schema of the whole architecture. We see the client on the internet on the top. Then we have a reverse proxy that's doing all the encryption for HTTPS. The VM supervisor. We can see the jailer with your VM running inside, with the custom init that's launching your process. On the right side, you can see the file system cache with the code archive, the runtime. And then here we have one immutable volume and one mutable volume in this example. On the left, bottom left, you have the connection to the internet. And then a bit higher, you have the guest API that's connected to an Aleph node and to extra properties from the host, for example, for signing messages. Now let's see in practice how to run a Python program on Aleph. So I have here a virtual machine that I already pre-configured, where I installed all the required dependencies. And I will just create a program and run it on Aleph. So the first thing I need to do is I'll create a directory to put my program in, so it's a bit more clean. So I'll create this directory. I will call it my program, and I'll just go inside this directory. And then I will create a file named main.py. And in this file, I will just put the example for Fast API, which I will open in the browser above me. So let's look at Fast API. So Fast API is a web framework that's designed to build APIs, to be asynchronous, and it's generating JSON schemas and a lot of things automatically, some user interfaces to experiment with the APIs, making it very nice to publish APIs to third parties. And you can use it in a way that's a bit similar to Flask if you're familiar with it, with decorators. As you can see, my internet connection is getting better, but it's still not completely resolved since yesterday. So while the page is loading, I will just copy the example of code from a note I have here. So here you can see I'm importing Fast API, and then you can see here app.get/. This is the when you get the root, the index page. It will just return message hello world, which I will change with hello Aleph, for example. And this app variable, that's the entry point for the ASGI program. So that's the entry point you need to specify in your settings. All right, we do have our program. Let's try to run it. So I'll use UVcorn. UVcorn is a source/ops bin. So I'm using my virtual environment where I install all the Python libraries to make them, put them in a different way than the rest of the system. So here, let's try using UVcorn. Yes. So I will specify the name of my file. It's main.py, so I'll just put main here. And then semicolon and app. App is the name of the entry point inside the main file. And I'll type --host 0.0.0.0, which will make my service listen to all interfaces instead of just localhost. Since this is running on a VM in the cloud, I should now be able to access this interface publicly. And here we have hello Aleph. So this is the really standard way of running a program. I'm renting this VM. It's running all the time, and it's answering my request here. So that's standard. But now let's try to move it to Aleph now that we've seen that the program is running. It looks good. I'll put it on Aleph. So I'll stop UVcorn. And then I will use the Aleph CLI. So if you type Aleph, you can see the different commands that are available using aleph-help. You can see we have a few options to install auto-completion, and then we have the main commands we can use. And here what we want to use is program. So we want to do Aleph program. Then we have to say where the program is. So here, in my case, I will go in the above directory. I will do Aleph program, and then I will do my program. So the whole directory will be copied, and then we'll use the same entry point, main semicolon app, that I used before. Let's press enter. So here you can see it created the SquashFS archive. And now it's asking me for the runtime I want to use. So I want to use the default Debian-based archive from Aleph, which is the one that it's suggesting here. So I'm just pressing enter. As you can see, if you want to have your own runtime, you can just customize it and pass its ID here. I do not want to add any volume to it, so I'll press enter again. And now it has been published. If I go on the Aleph Explorer, so explorer.aleph.im, I can see here there was a VM program that was uploaded, and here a store program. So this is a file containing the code. Exactly, the squashfs archive is here, and then we have the VM of the program. Let's have a look at it and see what's inside. So we can see first the ID of the VM, and then what's the address that sent it. Message type is a program, the channel confirmation. We have here a handy link, execute on aleph.sh. This is the same link that you can find on the left here. There are two URLs that are generated for you. The first one is aleph.sh, which is a VM executor that we provide to run your VMs on. And then here you can see the ID is exactly the same ID as we have here on the Explorer. So that's the ID of the VM. And in case you want to play with the routes, depending on the app you're running, we also provide here another URL where we have a host name that's different for each program. So this is the ID encoded in base 32. So it's not hexadecimal like the first one. It's the same value, but it's just encoded differently in base 32. So these will give you the same results unless if you are matching the routes inside your VM. For example, if you have in your HTML href equals /, then this will be more convenient if you have a host name that's dedicated to your VM. Let's have a look a bit at the message that was posted on Aleph. So here we can see the address that posted the VM, when it was, the type of message. Then we have the code. We can see it was encoded in squashfs format. The entry point is here. You can find it here. And that's the reference where it's stored. And use latest means that if you update this archive by referencing this one, so there is a way of amending files on Aleph, then it will automatically update your VM and the new version will start running. On HTTP, so this means that you can launch this VM using HTTP calls. Environment, so these are a few extra settings. You can define it if it's supposed to be reproducible, if the VM is supposed to have access to the internet or not, access to the Aleph API or not, access to the shared cache that I will describe a bit later or not. Then we have the resources, the number of CPUs, the memory, the number of seconds that it's supposed to run for. And then here we have the runtime. So we have a reference to that runtime. We also have this use latest. So if the runtime is updated, your VM will also be updated and restarted. And we have a small comment here next to it to know which runtime it's using. It's something that's hard-coded in Aleph client. You can override it, and you can see here it's slightly obsolete because we switched to Debian. And then here you can have the volumes. So if you have multiple volumes, same thing. If you have read-only volumes and one of them is uploaded, then your VM will be restarted, automatically updated as well. Now let's see if it's working. So we'll click on the link and see if the VM supervisor is running at the moment. And we can see here, hello Aleph. And the URL here, we can see it's the long version. So our program is running and it's responding. And I don't know if you counted, I think it took a bit less than half a second to start the VM, start the program, and get the response all the way to here. We can also try to use the URLs here with the base 32. And since here the VM was already started, it's almost instant. It just takes the time to go to the server and back. There is no extra latency at the moment. At some point, the server will tear the VM down, and then you will restart it on demand when needed. You can also update a program. So this is still in alpha, so there is no guarantee that it will work. But you can update a program and then have a new version deployed automatically. So let's try it. I'll update my program/main. And I will say hello Aleph community, for example. So I'll just save this file. I have the new version. I could try it locally again. I'll just try to publish it. So here, what I need is I need the hash of my program. Let's start with 8EB here. So I'll do aleph update. Then I will put the hash of my VM. And then I will just put the directory. And the Aleph client will automatically load the previous version, extract the entry point and everything. So you just need to specify what has changed. Let's do this. And now we have here, that's the store message of the new code. So the VM has been published, the new code has been published. Let's see if it works. And we can see that it didn't work instantly. It took a few seconds, and we have the new version already up. So here we have these changes that are pushed, and the new version is already running. And that's it to run a Python program on Aleph. So you have, you can look at if you look at the wiki, you will find some extra documentation on more advanced usage. So you have the tutorial, and at the bottom you will find some advanced usage as well. So you can, this will describe how you can, for example, access Aleph messages directly, how you can push, how you will be able to publish Aleph messages, how you can work with the shared cache. So the shared cache is basically a key value store where you can store values that are available only to your VM, but with really good performance. It's a bit like a persistent volume on a host, but it's designed to store small values like counters, small variables. Usually you don't always need to create a database in a volume and have a fixed size. So if you have just a few small variables, you can put them in this key value store. It's really handy for small things like counters, some small numbers to keep on, for example. And there is an interface, so you can just access them using the Aleph client library in the VM part of the library. It's also documenting how you can create these volumes. So here you can create your directory using mk-fs. Then if you want to publish big files, also if your program is big, then you cannot upload it directly to Aleph. You need to use IPFS, and this is documenting how you can do this. So you can start the IPFS daemon, add your volume to IPFS, and then you can use the aleph pin command to pin your IPFS hash on Aleph. And yeah, so that's mostly. One thing you will need to consider is if I type ls here, I have this device.key, and that's very important. Here it's a demo, so I will just look at it, but you should never publish the content of this file. This is in binary encoding. This is the private key that's used to sign the program that I just uploaded. So if there is no key, it will create one, else it will use the one that's here. That's how I could update my program. The sender was the same because the device.key was the same. If I remove it, I won't be able to, if I lose this key, I will not be able to update my program anymore. So it's something to keep secret, keep backups off. I guess if you're playing with blockchains, you're already used to this familiarity. So keep your private key secret. We create one in case you don't have one. And it's in this file named device.key.
Thanks for the presentation, Hugo. This was great. Um, I would say if there are more questions, please join our Telegram group we created for this. I will share it again here in the Twitch chat, and then we will be looking forward to hearing about you and seeing what you guys are trying to build on the system. So thank you all for joining, and hope to see you in the chat.